Hello everybody. Let us look at the solution of the radiative transfer equation today. We defined specific intensity. We defined a few things including specific intensity, and we wrote down how the specific intensity changes as the radiation propagates through the medium, and that was given in terms of the radiative transfer equation. So this I am writing down the radiative transfer equation that we arrived at the last lecture. So here, let me remind you of several things. S nu is given by the ratio of J nu and alpha nu. This we gave a name, we call it source function. And d tau nu is alpha nu times ds. So tau is optical depth or opacity. I nu is essentially our specific intensity, and what we are trying to do is to solve this equation today. Let me draw the picture. The picture is that there is some source over here. At this point, tau is 0. And remember that this is one-dimensional radiative transfer equation. Let me emphasize that. And this source is emitting with intensity I nu 0. If there is no medium, we have seen that I nu 0 is what we would have observed, but there is some medium in between. Because of that, that medium is emitting and absorbing. Because of that, what I get here is I nu. The medium has a property which is S nu. It's a property of the medium. Tau nu is also a property of the medium, and it changes as the light goes in the right hand side in this particular picture. So this is my observer. So this is the picture I have, and how I nu changes is given by this equation, the radiative transfer equation. We'll try to essentially solve this radiative transfer equation today. So let's proceed. So in between, at any point, I will denote this as with primes. At this point, tau will be tau nu. Okay, that is how you do differentiation and integration usually. These are the running variables which I have written in terms of primes. So let us look at the differential equation, and I will write this with both the i's in the same side. And let's multiply this with e to the tau nu. This is a very celebrated process of solving differential equation of this type. I'm just using it here. So what I have done here is that I have bring that I nu in which was in the right hand side with a negative sign in the left hand side, so it has become with a plus sign, and multiplied both sides with e to the tau nu. So let's see how to manipulate this now. The left hand side I can write in the following way. I can write total derivative of I nu e to the tau nu. The right hand side remains as it is. let's check if I get back the upper line from the lower line. So if I start doing the derivative, I take derivative of I nu, so that is d I nu d tau nu, keeping the other term constant. So that gives me the first term in the upper line. And the second, and when I take the derivative of e to the tau nu, I just get e to the tau nu. That times I nu is the second term in the upper line. So these two lines are consistent with each other. Now I can write it as an integral, and that will serve our purpose of solving this. This is I nu e to the tau nu. Integral is over that. And what is the value of I nu e to the tau nu at the point in the source? So because from there I am integrating. At the source, tau nu is 0, so e to the 0 is 1. So I have only I nu 0. And on the other hand, it is obviously I nu e to the tau nu itself. So this is I nu 0 in the lower limit and I nu e to the tau nu here. In the right hand side, I get this integral e to the tau nu, right, with a prime because it's a running variable, s nu prime, which is also a function of tau nu, remember, d tau nu prime. And the integral is over 0 because at the source it is 0, at the observer it is tau nu. The left integral is straightforward to do. If I do, I will get, so these are, again I should write with primes there. So I nu e to the tau nu minus I nu 0 equals 0 to tau nu e to the tau nu prime s nu prime d tau nu prime. And as I want I nu in terms of everything else, so my solution I can write in this form. So I divide everything by e to the tau nu and also bring that minus I nu 0 in the right hand side back to the right hand side. So this is e to the minus tau nu plus e to the minus tau nu times the integral. The integral, obviously I cannot do anything unless I know s nu as a function of tau nu. That will depend on what type of source we are using. It's a source function which I don't have any idea a priori before we start doing a specific problem. So this is the solution, general solution of the one-dimensional radiative transfer equation. So let me put it in a box. Okay. Now obviously, just looking at it, we don't get much understanding. So we'll take a special case. The special case in which we will try to understand this solution is the case where, so special case, what is a special case? S nu, which is supposed to depend on tau nu, doesn't depend on tau nu. It's basically constant. So I could have written s nu 0 here, but I'm not writing. So it's a constant essentially. So if it's a constant, it can come out of the integral. And then you can do the integral because the integral is just over tau nu. So let's see what will I get. So I'll get I nu equals I nu at the source e to the minus tau nu. S nu comes out, so just write S nu. And then let's try to write the rest of it. E to the minus tau nu times the result of the integral. So if I do the integral, I will get what? I will get e to the tau nu first, and in the lower limit I will get tau nu is 0, so I'll get 1. So for this special case, the special solution, this is just for the sake of understanding, remember, but this will give us an enormous insight shortly. The first term is just S nu, and the second term is 1 minus e to the minus tau nu. So this is the solution. What we'll try to do now is we'll try to understand these terms, these three terms. So let's try to do that first. So let me draw the picture again here. So this is my source, where I said the intensity is I nu 0. And obviously tau is 0 at the source. And then I have this medium. And here I have this I nu. Okay. This I nu 0 goes through the medium, and a part of it is lost because of the absorption in the medium. So that I nu 0 is lost by absorption, and the absorption factor is e to the minus tau nu. So that gives me this term. Then the medium adds. So this is I nu 0 absorption there. Adds to the radiation. That is essentially this term. But you see, if the medium adds a radiation here, then in the rest of the path of the radiation, some of it can get absorbed. So that is this term. So part gets absorbed. That is this term. So this is sometimes called self-absorption. Because the medium is absorbing what it is trying to produce itself. So that's why self-absorption. Okay, so that is what is happening. So you have a background source, which intensity I nu 0. As that light is coming through the medium, part of it is getting absorbed by the medium. So I get the first term, I nu 0 to the minus tau. Then the medium adds a little bit radiation to it, so that is S nu. That's why it's called a source function. And then part of that radiation which the medium itself adds gets absorbed. So that's this self-absorption. That's the third term. All right. So this is what I mean by these cases. Now what we'll do is we'll take different limits on tau nu and see how this equation behaves. And from that we will have very, very interesting and important understanding between thermal and non-thermal radiation. So what we are embarking on now, perspective of thermal and non-thermal radiation. So this is what we'll discuss now. What I assume here in this discussion is that all of you have learned a little bit of thermodynamics and things like black body radiation in some earlier cases, earlier studies. So let's take the case when tau is much greater than 1. Much greater than 1. So e to the minus tau is essentially 0. So what happens to this equation? What is the I nu that I will get? I nu will be, you see, e to the minus tau comes here and it comes here. These two will be 0. What all I will be left with is just S nu. Source function gives all the intensity. The background information is lost. Right? The background was I nu 0, that is not there anymore when I observe it. So that information is completely lost. How does it happen? How the information is lost? So that is a very important thing, and that will give us very deep understanding on this type of radiation. So what is happening in this particular case? So imagine that these photons are coming from the background source, and here I have this observers. Now tau or d tau, if you remember, is given by alpha nu ds, and alpha nu is nothing but n sigma nu. So d tau large means ds is large, or alpha nu is large, or both are large, which means either of these three large means there are a lot of collisions. So these photons comes and then they get collided with one or these atoms, and they basically, the energy of the photon gets equally distributed in these atoms. So the energy, the photon might have some energy. Now these atoms which you are looking at here, they will get the energy of the photon distributed, and these atoms come into thermal equilibrium with photon. So the total energy is distributed in all the possible degrees of freedom of the system. So I write Tg, which is the temperature of the gas, but its thermal equilibrium in photon. So that temperature, the photon temperature is same as that of the gas. So I call it T gamma. And I will just write it as T for the time being. So basically, the radiation has collided so many times with the atoms there, and then the atoms may have radiated again, and those gets absorbed. And this has happened so many times because tau is large, the number of collision is large, that the energy gets enough time, energy of the radiation, and the atoms get enough time to redistribute amongst themselves. And that is because, that is the reason why, that is why the background information is lost. This is like when you are looking at the wall in your room right now, there may be a lot of photons falling into that wall from the other room. But those photons are not passing through the wall. They're all getting absorbed inside. And if they had some energy, now the wall has gained that energy. That is why in the summertime, our walls and the roofs get hot as a lot of sun rays fall into them. And then after sometimes they start re-radiating inside and we feel very warm. We feel not warm but hot. So that's what is happening when there is a lot of collision, which is the case when the optical depth is much, much greater than 1. Now, if the photon has come to a thermal equilibrium at a temperature T, you know that in thermodynamics we have laws by Kirchhoff which tells us what is supposed to be the intensity of the radiation. So let me write down Kirchhoff's first law. So what is this? In thermal equilibrium, the ratio of the to absorption coefficient so thermal equilibrium at temperature T is that of a black body at that temperature. So it only depends on that temperature. So what has happened because of so many collisions is essentially that this gas now will behave like a black body. And as I said, that you must have studied what is the intensity that comes out of a black body. So hence, I can now write down, we can write down what is S nu, the source function. So the source function S nu is nothing but the intensity, specific intensity of a black body at a temperature T, the same temperature as we have talking about. So this is specific intensity of a black body at temperature T. So what is specific intensity of a black body at temperature T? It is 2h nu cube by c square 1 by e to the h nu by kt. K is the Boltzmann constant Not emphasizing these things, as you know already. This. So I have got what is the source function. Okay, so let me go through the logic once more. So we said that we are talking about the case when tau is much greater than 1. If tau is much greater than 1, just using the radiative transfer equation, we figure out that irrespective of what background radiation is there, that information is completely wiped out. What we will get as the intensity out of the cloud or out of the medium is the source function of the medium. Then we said, well, tau much greater than 1 means a lots of collision between photons and the particles in the medium, and often calling it a gas. And once that happens, the gas and the photons will come into thermal equilibrium at some temperature, so say T. And in thermal equilibrium, at a given temperature, Kirchhoff's law tells us that the emission to the absorption coefficient ratio is constant and is that of a black body. So the emission to absorption coefficient ratio, which we call the source function, in that will be the specific intensity of a black body at the temperature in which the gas is now. So I can write down what is S nu from, because I know what is a black body specific intensity. Okay, nice. So this is so far so good. And it's obvious that we'll look at the next thing now, which is the opposite limit. Tau nu is much less than 1. Very less, obviously very less collision. Here, for the sake of understanding, we also consider that I nu 0 is 0. So there is no background source at all. It's all that gas, all that medium that is emitting and doing self-absorption. So in this case, let's see what will be my I nu. Let's go back to the radiative transfer equation. So I nu 0 is 0 means the first term does not exist. And the second term is S nu into 1 minus e to the minus tau nu. So let me first write that down. S nu into 1 minus e to the minus tau nu. But tau nu much small, tau nu much smaller than 1 means I can write e to the minus tau nu. I can do Taylor expansion on the exponential, and this will be just 1 minus tau nu. So which means that I nu then in this particular example is S nu into 1 minus 1 plus tau nu, so S nu times tau nu. So that is in this particular case. And just to remind you, so this is much less than 1. Okay, so let's see what's happening to this medium. So I have only the medium, remember, I don't have anything as a source. So I have this medium, and it's kind of, if you wish, rarefied, very less number of collisions with the photon. Less collision between the photon that the medium emit and so this medium can spontaneously emit some photons, that is the source or only source of the photon now. So, but there is very less collision with those photons and the medium itself. Okay. So in that case, it may be maybe there is enough collision between the particles of the medium. Particles, let's say particles. It's not a very waterproof term, but it's all right for our understanding. So that may take the medium to thermal equilibrium. A temperature, say Tg. G stands for gas. Okay, so the medium can be in a thermal equilibrium at a temperature Tg. So corresponding source function is this, right? The intensity of a black body radiation at Tg. But see, because there is less collision between the gas in the medium or the medium and the photons that the medium has created, photons don't come to thermal equilibrium with the medium. So when I say photons, it essentially means radiation. Okay, so the photon is not in a thermal equilibrium, so not like black body. So its radiation will not be like black body. Okay, so what will be the radiation? So solution of radiative transfer, we have already seen what will be the radiation, right? The radiation in this case we have seen is S nu, and this is the S nu for that particular temperature. I could have emphasized it here, but not required really. Times tau g, times tau nu. And remember that tau nu is much less than 1, which means that I nu is less than S nu, which is this. So what have we found here? We found that the photons are not in thermal equilibrium. Their intensity is less than the intensity of a black body radiation at the temperature of the gas which has generated the photon. And that's essentially is Kirchhoff's second law. There are two H in Kirchhoff. I'm not very good at spellings, so there can be mistakes. Please correct them by yourself. So what is Kirchhoff's second law? It tells you that if the gas is not in thermal equilibrium, the intensity of radiation, and it's at all temperature, because you see this is true irrespective of which frequency, sorry, not temperature, which frequency you are looking at. So it's at all frequency, at all frequency is less than that of a black body at the temperature of the gas. Okay, I'm not absolutely aware if this is exactly the statement, but this is essentially the meaning of the Kirchhoff's second law. So what does it mean? It means, you remember how the black body curve looks like? So say I plot I nu as a function of nu. It looks something like this, right? So this is the case tau nu much greater than 1 thermal radiation. If it is not a black body, then you can see something like that. In all frequencies, it will be less than that of a black body, the intensity. This is non-thermal radiation. Okay. So it's not required to be much less than 1. You can see if less than 1, then only it will survive. Then only it will work. Okay. So what I have drawn here are like spectral lines. So you see the spectral lines, if somebody asks you to draw the spectral lines for say something which, so let's say for example there is a star which is emitting, which usually emits like black body, and somebody asks you to draw spectral lines, emission lines on the stars. So they cannot go above the black body spectra of the star. Okay. There are certain cases where there is some departure from this law. It's not actually departure, but what we have considered as emission and absorption. In certain cases, absorption can work like an emission, but let us not go into those right now. But almost always this holds. Okay, so we have looked at the cases, two cases. So let's see what we have looked at from the beginning. We have first worked out a formal solution of the radiative transfer equation, and then we considered a special case for understanding purposes. Then we considered cases of that special case to understand thermal and non-thermal radiation. It turns out where tau is much greater than 1, what we get is thermal radiation. So S nu is essentially the specific intensity of a black body kept at the temperature of the gas. On the other hand, if tau nu is less than 1 or much less than 1, then we get non-thermal radiation because the gas and the radiation doesn't get thermalized with the gas. If the gas may be thermalized at a temperature, say Tg, so it will have a Maxwell-Boltzmann velocity distribution with the temperature Tg, but the intensity that we will see out of the intensity of light coming out of that gas will be less than that of a black body at that temperature Tg. And that's what is Kirchhoff's second law. Okay. The rest of the time today, we'll try to discuss a particular system which gives rise to such emission and absorptions. So far, we have been talking about radiative transfer without reference to what are these atomic emitters or absorbers are. So there can be two ways you can generalize. You can think about this. So atomic, and I write within quotes because as you'll see that this is not necessarily atomic. We have been calling it atomic just because I called it atomic. So there can be two cases. One is transition between energy levels. So this can be in an atom, in a molecule, can be rotational, vibrational levels also. There can be many different things, but this is essentially transition between energy levels. This is a quantum phenomenon. It's essentially a quantum phenomenon. There is no classical counterpart of it. It can be the Lyman alpha transition, for example. The other is acceleration. When I say acceleration, it can also mean deceleration of charged particles. That you have learned in your electrodynamics course, that acceleration of charged particles gives rise to radiation. So the first one gives kind of discrete energy levels. This kind of gives continuous spectra. So if the energy levels are discrete, the frequency, it will only peak at a certain frequency. The intensity will be there only at a certain frequency. Other frequency, it will be not there. In case of the acceleration of charged particles, you will see it's more like a continuous spectra that you will get. So acceleration of charged particle will give you this baseline continuous spectra that you see here, and the discrete and atomic transitions or transition between energy levels will give you this peaks kind of thing. So in the rest of the lectures about radiative transfer, we'll only consider this. The cases to look at for two, you may have already done in your electrodynamics, which are important for astronomy, are the Bremsstrahlung radiation and the synchrotron radiation. But in this particular course, we'll not have time to talk about those. So today, in the rest of the time, I will start a discussion on a two-level atom system, and we'll follow it on from in the next class. So what do we have here? We have two energy levels, and conveniently I call it up and this lower. Energy here is E up, energy here is E low. Okay, just like two levels in the hydrogen atom. The difference in these two energy, you know that Bohr's quantization rule will be h nu. H is the Planck's constant, obvious thing. Now, as we go along, we'll deal with different types of transitions between these two energy levels. First, let us talk about absorptions. The next thing we'll say is called stimulated emission. It's like absorption in all sense. Just happens in the opposite way. And the last one is spontaneous emission. To start with, we have the number density of the atoms which are in the upper level is Nu, and the number density of the atoms which are in lower level is Nl. Okay, Nu plus Nl is the total number density. So what happens in absorption? In absorption, you have these two levels, the same level everywhere actually. You have the photon of energy h nu has fallen into the lower level, and because of that, one atom from the lower level go to the upper level. The question we are asking is how many atoms will go from the lower level to upper level. So what will it depend on? It will depend on the radiation, because it's a process which is induced by radiation. This is one of the type of the process we talked about in the last lecture. So it's going to the upper level and it's induced by radiation. So let me write a radiation energy density here. So it will depend on the radiation energy density. If there is no atom available at the lower level, obviously nothing can go to the upper level, which essentially means that it will depend on how many atoms are there in the lower level. And then it's an atomic process, and as you know that all atomic processes, there is a probability associated with it. So it will depend on that probability. And that probability also hides all the other factors that you need to make it work. So this number, whatever I have written here, is the number of atoms that is changing their levels from the lower level to the upper level. So I asked the question that, and this also have a per unit time. So when I say it's a probability, it gives you how much of this happens in a unit time. So this dnu dt, which is the gain in the atoms which are in the upper level per unit time, the first term that I will get is this, because this is the atoms are going from lower to upper, so the upper level density is increasing. Next, let us come to the stimulated emission. The stimulated emission, what happens is just the opposite. And this is what I said in the last lecture also. This Einstein gave this concept. So what's happening is that a photon of exact energy h nu falling in the upper level, which is inducing an emission transition. So this goes down here and another photon is produced. Okay, so I'm just drawing two wiggly lines just to remind you that there are two photons produced. So first of all, this decreases the density from the upper level, so I should write this with a minus sign. And what will it depend on? Just like before, it will depend on the energy density, obviously. Now the number density in the upper level, if there is none, there cannot be any such transition. And I will have a coefficient. Now I am writing it from upper to lower because that's what is happening in this case. So these coefficients are called Einstein coefficients because he introduced these. And it's remarkable that he introduced these in 1905. Bohr's theory came a lot later. So this basic understanding of how this two-level system will work actually came before we ever knew that there are two-level systems. And that's why Einstein is so remarkable, probably. This is the method that was later used to understand lasers. But that is a more complicated system. Here we have two-level systems. Okay, what else can happen? I can have a spontaneous emission, which is not assisted by any radiation, just the atom decides to go from the upper level to the lower level. and that will again decrease the number density in the upper level. It will obviously not, now it doesn't depend on nu because it doesn't depend on radiation, it is spontaneous, but it depends on the number density of the upper level. If there is none, no transition will be possible. And now I will need another coefficient here, which will definitely be different than this, because this one requires the radiation to be there, and both of these require radiation. Because of them, we leveled it with B. So this one I will level with A. So this is AUL. Okay. So this is giving me this type of things are called rate equations. This is a rate equation. So what happens in thermal equilibrium? See, let's assume that this atom is in thermal equilibrium. It's not one atom, but many atoms, they're in thermal equilibrium. They're equilibrium with the radiation. So in that case, we know that the spectra will be that of a black body. If I fix a certain frequency, which is the frequency of this transition, the intensity of that frequency is fixed, which essentially means by no means I am allowed to add or subtract any photon from the photons which are already available. So if that is the case, then in the thermal equilibrium, there cannot be any up transition which eats up a photon, or a down transition which produces a photon. So this spontaneous emission will produce a photon, right? So the net of this is 0. So in thermal equilibrium, this is 0. So that means that right hand side is 0. And now I can write down what is u nu for thermal equilibrium in terms of everything else. What is it? So it is AUL by so what we have to do is we have to take things from left hand side to the right hand side, etc., etc. Finally, we will be able to write down what is the ratio of what is u nu. So what you will get is the following. So NL, so which is this. So AUL has NU, so that I have taken here. Okay, so what you have done, you have divided everything by NU. So when I take U nu in the left hand side, so this remains with BUL. But you see, this is in thermal equilibrium, which essentially means that this should be equals to the energy density of a black body. There is no other way, because thermal equilibrium, we said that the radiation is that of a black body, and this should be now equals to the energy density of a black body, right? So what is the energy density of a black body? The energy density of a black body is 8 by h nu cube. This is again Planck's formula, so I guess that you are already familiar with this. And here I have assumed isotropic radiation. So this u nu is integrated over all directions. Okay. Now there is one more thing that we know. This is from the Maxwell's distribution, that probability, I can note down the probability of these numbers. So Maxwell distribution tells you NL is going to be GL times e to the minus EL by KBT. Similarly, NU is GU. Now this GL and GU are the multiplicities of the state. Means how many different ways in the atomic configuration you can reach that energy level. So that is GL or GU. Okay. So this gives me NL by NU, which is present here, is GL by GU e to the power EU minus EL by KBT. EU minus EL is nothing but H nu, because that is the energy difference between the two levels. So NL by NU is GL by GU e to the H nu by KT. So now that's what I will write for U nu over here. So let us do that. So U nu is AUL, and I divide that by BUL here. We'll see why. Divided by, this term becomes 1, and NL by NU becomes GL by GU e to the H nu by KT. And again that has to be equals to 8 pi H nu cube CQ 1 by e to the H nu by KBT. Sometimes I'm writing K, sometimes I'm writing KB. They're same, Boltzmann constant. And now comparing we realize that AUL by BUL is this factor 8 pi H nu cube by CQ. So this is not just GL by GU, but I also will have BLU by BUL, right? So let me organize it a little bit and move it a little bit here. Fine. Which means that GL by GU also has to be BUL by BLU. So what happens here? So the multiplicities are usually known for a given atomic level, which means that BL and BAUL and BLU ratio is fixed. And AUL, this tells you how is AUL related to BUL. So out of these three Einstein's A and B coefficients, I need to know only one. So if I know only AUL, which is the one which is usually calculated, I will be able to find out all these three coefficients. And once I find out these coefficients, you see then what will happen. These two are the cases where the radiation dependence is there. These two will essentially give you the absorption coefficient. And this is the case where spontaneous emission is involved. So this will give you the spontaneous emission coefficient. It will obviously depend on which level transition you are looking at. But other than that, I'll be able to calculate these coefficients now, given a particular transition I'm looking at. So just for an example, it's not very apparent from here. Maybe it is apparent from in this particular case. See, this is NU times AUL. If I just do a dimensional analysis quickly, I see that in the left hand side I have NU into T to the power minus 1, right? The time inverse is there. So AUL should be per unit time, given in per unit time. Essentially what it gives is, so AUL essentially gives you probability of transition per unit time. That is nothing but is the thing which is responsible for what we usually call in spectroscopy selection rules. This is the thing which decides the selection rules. For example, if I consider the Lyman alpha transition of hydrogen atom, which is n is changing from 2 to 1, the lambda, the wavelength for Lyman alpha is 1215 angstrom. Using the wave functions of the atomic energy levels, one can calculate this number. And it comes out to be for Lyman alpha 6.3 into 10 to the 8 per second. So it essentially means that if you have one atom, it can go this transition 6.3 times, 6.3 into 10 to the 8 times in every second. So this is a highly probable transition. Okay. Anyway, we are running a little bit over time, so I'll stop here. We'll pick it up from here in the next class. What we have done in this particular class is we have looked at the thermal and non-thermal radiation in the view of the solution of radiative transfer equation and had a little bit of insight in a two levels.